Hello everyone. Today I wanted to look at further maths A2 differential equations. In this video I will go through everything you need to know about differential equations, and we'll go through it step by step to all the types of questions they can ask, and I'll give you some examples as well. So first I want to start off with first order differential equations. So this can be either a linear differential equation or homogeneous or non-homogeneous differential equation. But in the further math syllabus, you will only look at linear differential equation, not non-linear differential equations. So you don't need to worry about not linear differential equations. So in the first order differential equations, linear, you can either have homogeneous or non-homogeneous differential equations. Now, what do these terms mean? Well, start off by looking at what is the general formula for differential equations. So first order, by order we mean the derivative, the highest derivative that is mentioned in the equation. If it was second order, then it would be the second derivative, but since it's first order, the highest derivative here is the first derivative. So this is the general formula of a first order linear differential equation, and A, B, C and D are constants here. The reason why I put B and C as separate constants because I just wanted to show you as a function of y and a function of x multiplied together. But obviously since B and C are constants, you can write this as one whole constant, but you don't need to worry about that. I just wanted to make it more clear. That's why I separated them. And here it is said B and C can equate to one constant, obviously. So by homogeneous, we mean that D is equal to 0. So the general equation would be ax dy dx minus by cx equals 0. So D is equal to 0. So there is nothing on this right hand side. And non-homogeneous is when D does not equal to 0. So the general equation is this. So these are two types of first order linear differential equation that you can get to solve. Now to find the general solution, the general y to this differential equation, because when you are solving differential equations, you are solving for y equals to a function of x. So the general y has to equate to the y complementary function plus the y particular function. Now I know this is probably very new to you, but just keep this in mind and I will go deeper into what this means. So there's two ways to solve a differential equation, first order linear differential equation. One way is to separate the variables, the other way is the integrating factor. Now I know it might be a little confusing right now because of everything that you've been introduced to, because this is probably very new to you, but just stick with me here. Just remember this, and these are the two ways that we're going to look at, and I will get into every single step very clearly, and you will understand by the end. So make sure you watch this video till the end. So let's look at the first method to solve first order linear differential equations. So that is separating variables. Now here is an example of a non-homogeneous differential equation, because this right hand side is not 0, so D is actually not 0. And one thing I forgot to mention is that D does not necessarily have to be, so here D is a constant, but on the right hand side you don't necessarily have to always have a constant. It could be any function of x. So here we have a function of x on the right hand side. So here are the steps that you need to look at to solving this differential equation. Number one is to write the homogeneous equation. So since this is not 0, this is a non-homogeneous equation. So all we have to do is equate this left-hand side to 0 to make it a homogeneous equation. And solving the homogeneous equation gives you the y complementary, and this relates to what I've said here. The general y, which is our goal to solve this differential equation, is finding the y complementary plus the y particular. So solving a homogeneous equation gives you the y complementary function. If, for instance, this equation was homogeneous from the beginning and it was always equal to 0 and there was nothing on this right hand side, then your general equation, your general y would just be y complementary. It would not have a y particular equation. The y particular equation comes from the second step, which I will show you, which gives you the y particular. So all you have to do is add step 1 to step 2 to get the general y that we are looking for. So before we get into that, let's look at this step by step. So solving this homogeneous equation again gives us the y complementary, and how you solve this is by separating the variables. So we have this equal to 0. Now what we can do is bring this to the left hand side and then divide it by 6x, and then you can integrate both sides with dy here and dx here. So with respect to y here and with respect to x here, because this is a function of y and this is a function of x. And then obviously you get ln y is equal to minus ln x over 3 plus c. So if you simplify this further, you get this plus the constant, and then simplify this again by adding the ln, and since this is a constant, this just becomes 3a. And remember the rule of logarithms: when you add, you are multiplying what's on the inside. So you get 3a over x, and then you get y equals bx. So I just made 3a into one constant b. So that is what you get for your y complementary. So this is what you've solved for your y complementary. Now to find your y particular, we have to use what is called a trial function. Now, I'm just going to give you a brief introduction to how you use the trial function, but I will explain more in depth further on in this video of how you know what trial function to use. So the trial function uses y equals a ln x plus b. Now the reason why we use this is because this is the general form of your function on the right hand side. And the reason why we add b is because you can write this as, because there can be an imaginary plus 0 here. So we need to account for this imaginary in the general form. So the general form of this right hand side can be written as y equals a ln x plus b, and this is what we call the trial function. Now with our trial function, what we can do is differentiate it, and we get a over ln x. And now what we do with the trial function to solve for the y particular equation, you have your dy and your y here, and now what we can use is substitute these two into our original function, into our original differential equation. So we have 6x multiplied by a over x, which is the dy here, and then 2 multiplied by the y, which is this trial function, and then 3 ln x on the right hand side. So this is what we get. And how to solve this. Now how we solve this is by comparing coefficients. So we have 2a here and we have 3 here. So you can say 2a is equal to 3, and we get a is equal to 3 over 2. And then we have 2a plus 2b here, but it has to be compared to 0 because we have no term on the right hand side for that. So we have 2a plus 2b equals 0. And then we get b equals minus 9 over 2, and this is our particular integral. So this, what we've solved here for a and b, is for this trial function. We just solved a and b from here. So we can say now that our particular integral is y plus a, which is now we've solved 3 over 2 ln x minus 9 over 2, which was our b. This is our particular integral. So the general solution would be this particular integral plus the y complementary that we found from before, which is b over x. So y general is b over x plus 3 over 2 ln x minus 9 over 2. So I hope that makes sense. And that is the separating variables method. Now you can't always use separating variables, and that is when you have to use the integrating factor. Now the reason why we use an integrating factor is when we have x on the y term. So the general form would be, we're still looking at first order linear differential equation. So the general form in which the differential equation can be, for which you use the integrating factor, can be this, or rather, to put it more clearly, dy dx plus a function of x, y plus a function of g. So two different functions basically. And you have an x on the y term, which is why this function of x comes here. If you look at the previous example we looked at, here there was no function of x, it was only a constant. So that's why we can use the separating variables method. But here, for integrating factor, we can only use this when you have a function of x. This also works for when you don't have a function of x, but then you can't use separating variables for when you have a function of x. So integrating factor works with both, but separating variables only works when you don't have a function of x. So I hope that's clear. Now let's look at an example here. So we have cos x dy dx minus 2y sine x equals 3. So first step is to write in the required form. So you always have to do this before performing the technique of integrating factor. So what we have to do is we have to make it into the general form of this. So we divide cos x by each term, and we get sine x over cos x, which becomes tan, and 3 over cos x, which becomes sec. Now, this is where the integrating factor comes in. Ix is what we call the integrating factor. And we have to and this integrating factor, the general way to calculate this is by doing e integral of the function of x. So minus 2 tan x. So this is what we use. So generally, the integrating factor can be calculated as e integral of f of x dx. This is how you find the integrating factor. And so this is useful because we have to use this into the differential equations to calculate it. We will go into that deeper as we look into this example. So first, let's just solve this. So integral of minus 2 tan x would give us minus 2 ln sec x. And then we can bring the 2 on top, and then we get ln cos squared x, e to the ln cos squared x, and obviously this cancels out, so we only get cos squared x. So this is our integrating factor. Now what we do with this integrating factor is we multiply it by each term of the differential equation. So we multiply dy dx by the integrating factor, and then we multiply this term by the integrating factor, and this is just the simplified form that you get. And then we multiply 3 over cos x by the integrating factor, and this is the simplified form of what you get. And then I've just simplified this further by using trig identities. Sure, you can see this clearly because all I've done is replace this with sine x over cos x, and then the cos cancels out. And then here I've just replaced it with 1 over cos x, and the cos cancels out. So we can write this solution. Now there is a whole proof for this which you can look at, but this is basically the shortcut that you can use to solve these equations. The reason why we use the integrating factor, the reason why it works, requires a lot of proof to prove. So you can look into those in separate videos that I can link down in the description, but in your level, it might be a little difficult to understand why we use these. That's why we just go through it step by step, and these steps just sort of stay the same for all the questions you do, and by practice they get familiar. But if you really want to look into why this works, then I will try and find video solutions showing the proof for it. But this is just the method and how you use it. And what we use is this function, which is in front of the dy dx, and we use the variable from this second term. But this obviously changes with what differential equation you're given. If it was, for example, dz over dx, then obviously this won't be y, this would be z. But the main thing is to use the variable which you are given and then multiply by the function in front of the dy dx, and we equate this to the right hand side, which stays the same here. So I hope you can see how we rearrange these terms to try and solve them. Now again, the reason why this works requires a lot of proof, but this is just the general step which you do. Since we have a d over dx here, we can integrate the right hand side, and this is what we get. And then we can just do y over cos squared x equals 3 sine x, we've just integrated this, plus c, and then we just divide cos squared x on both terms to find y with respect to x. So this is how we use the integrating factor. As you can see here, the complication of the y complementary and the y particular is not in the integrating factor. All you have to do is follow these steps and you get your final answer immediately. So that is what's nice about the integrating factor, but again, you have to see what differential equation you're given and decide what method you want to use. Now I want to look at an example which requires a substitution case. Now these questions can be asked in your exam, so that's why I wanted to look at one of these questions, because they are in your further math syllabus. So let's look at this example. So you have this differential equation. This is a second order differential equation, but we've only looked at the methods for first order linear differential equations. So how do we solve this using the first order linear differential equation methods? Well, you can use a substitution. Now the substitution that you use is going to be given in your exams. They won't make it that hard that you have to come up with a substitution yourself. So here in the exam question that I'm looking at, they've given us the substitution of u equals dy over dx minus 2x. Now how we can use this substitution is by differentiating it and getting du over dx, and then to differentiate dy over dx, it just becomes the second derivative, and then again, if you're differentiating with respect to x, then you just get minus 2 here. So we have these two, which we can use as substitution. But over here we have to do a little bit of rearranging, because we want to substitute the dy over dx, not the du over dx. So let me just move the star down, because this is the equation that we want to focus on. Alright, now looking back into our original equation, we can substitute these two into the equation, and as you can see, this just becomes a first order linear differential equation. So all I've done here is substituted what we know here, and I have just simplified it. You can see the simplifications here, just directly simplified, and then rearranged to get to here. So now we have this to work with, and this is our starting point for solving the differential equation, the first order linear differential equation. So what I can do is use the integrating factor. Now all I've done is I've rearranged it into the general form of integrating factor that we've looked at. Remember, that was the first step, the first vital step that you have to do. Please don't miss this. You always have to rearrange it into the general form, or else you will get an entirely wrong answer. This is a very common mistake that students make, so make sure you don't make this mistake. Now what we've done is just calculated the integrating factor. Again, it's just e integral of this term right here. And don't forget your dx. Silly mistake from me. So this is what we started with, and this integrating this will give you ln x cubed plus 1. And this is just directly from the integrating fraction, and gives us a ln function. If you want to look at more of how you integrate and all the rules that you need to know integrating and differentiating the maths, I have that in my other video, which I will link down below. So make sure you practice your calculus before you go into differential equations, because it's very important that you've polished your integrating skills and your differentiating skills before we move on to this. So, and then we simplify this. All I've done is put the minus on top, and the e and the ln cancel out, and you get 1 over x cubed plus 1. Alright, and then again, following the same rules of integrating factor, we just multiply this term by every term of the differential equation. So we've multiplied it here and here and here as well. But since there was a 0 on the right hand side to the beginning, it stays 0. And all we've done here is use our variable, use the same variable, and the term multiplied by the du dx, multiply this together, and all I've done is integrate both sides, and this is what you end up with. And then remember, this was the substitution that we used. We substituted u, so we have to substitute back and use our starred equations right here, and we have to substitute back and we get this. I hope that is clear. And then I have just rearranged it for dy over dx, and we get this. And since we want a function of y, I have just integrated this, but obviously it's not correct to write that, so I've just integrated this. This is just a simple linear integration, and you get another constant d. And so we get our final answer for y, which is x squared plus c brackets 1 over 4 x to the power of 4 plus x plus d. And that is how you solve first order linear differential equations with a substitution. So next thing we're going to look at is second order linear differential equations. So the general form of the second order differential equation is this. Now, the reason why it's called second order is because the highest derivative is the second derivative in this differential equation. So how we solve this is first by finding the auxiliary equation. The auxiliary equation is basically the quadratic that you can form with this second order differential equation. All we've done is make lambda equal to dy over dx. And so we can solve this as a quadratic equation. Now this gives us the y complementary, and the solutions we get from this quadratic is what tells us what our y complementary will be. If we get, so these are the rules that you have to remember. There are 3 rules. There's 3 cases that a quadratic equation can give us. So one can be you have 2 different roots. Then your y complementary will be in this general form. A e to the power of the first root x plus b e to the power of the second root x. Again, these are the solutions to this quadratic equation, which you derive from this second order differential equation. The second case can be 1 repeated root. So for this, our y complementary will be in the form of a plus bx e to the lambda x. Again, this is the one singular solution, lambda, that you get from your quadratic equation. And the next solution, since we're doing further maths, is the complex roots. Now, this third case, so all you have to know is the general solution for this would be e to the alpha, which is the real part of the complex solution you get, plus a sine beta, which is the imaginary part of the complex solution you get, plus b cos beta x. That will be 3 cases in which you can use, and the 3 types of y complementary functions you can derive. Now you have to memorize these general forms to solve your second order linear differential equations. Now, as you know before, y general is our goal, and for that we need the y complementary plus the y particular. And using this auxiliary equation, we can find the y complementary, and now we have to look at how we find the y particular. Similar to the example we looked at before, we have to use a trial function for the y particular. Now, the trial function that we use is limited to these functions because this is all you get in your exams. These are all the questions they can ask, but of course the trial function is just a general form of what you have on the right hand side of your differential equation. By right hand side, I mean the g of x, as we mentioned in our general form before. So if you have, for g of x, or in this case I just wrote an f of x, but I guess I'll write this as g of x, so you can connect all the general forms I've given to you thus far. So if it is a linear function, then you would just replace your, so this is what is given in the function. So all you have to do is replace it with two different constants, which would be p and q. And then again, as we looked at the example before, we use different constants so we can equate the solutions and compare the coefficients and then solve for these constants to get our trial function. I will give you an example after this, just to make it clear, but these are just the rules that you have to remember. And this also applies for any other polynomial, so the general polynomial of the same order will be your trial function. So for example, if it was a quadratic, then it would just be p plus x squared plus qx plus, I don't know, d, any other constant. And if you get a function of a cos bx, then you need to use the trial function of this. As you can see here, they're both sine and cos used over here. This is mainly because if you differentiate the function of cos, you end up with a sine, and if you have a sine and you substitute into the differential equation, it will end up canceling each other out, so it doesn't work. That's why the trial function we use includes both cos and sine. And if you have a function of sine, then again you also use both cos and sine. So this is just something that you have to remember. If you have, the next one is if you have a function of e to the x, then you just have to replace the constant which is in front of the e, but this constant of x stays the same. So I hope it's clear how you transform, how you choose your trial functions depending on what function you have on the right hand side of the differential equation. So now another rule that you have to remember is if the trial function does not work, by does not work I mean if it cancels out once you substitute them into the equation, into the differential equation, then you can multiply the appropriate trial function with x. So for example, if you have e to the x and you use the trial function of pe to the x, then and it doesn't work, both sides cancel out once you substitute it into the differential equation, then you can multiply it by x and the function should work. Again, I will give you an example just in a moment so things are more clear to you. And this is usually when the trial function is part of the y complementary. So the trial function does not work when the trial function is part of the y complementary because, again, same reason, it cancels out on both sides, so the trial function does not work. Now let's look at an example to show you what I'm talking about. So if you have this second order differential equation, so first step is to find the y complementary, and again we do this by using the auxiliary equation by transforming this into a quadratic by just replacing these with lambda, so lambda squared and lambda, and we get two distinct roots. And looking back at the rules I gave to you before, if you have two distinct roots, then our complementary will be, so that we've found our complementary. Now let's find our y particular. So the trial function we use is pe to the bx. Now, how we use the trial function, again, as I briefly showed before, is you differentiate, and then you differentiate again, because you have the max order you have is the second order. So we need a second order to substitute into the differential equation. That's why you need the derivative and the second derivative to substitute back in. So here is how I have substituted it into our original equation, and then I've just simplified it, and then we compare the coefficients, and we get 9p, comparing p and whatever is in the front here. Obviously, since there's nothing in the front here, it's 1. So p is equal to minus 1 over 9. So our particular function is minus 1 over 9 e to the 2x. So our general solution we get is y equals our y complementary. So this is our y complementary, and the y particular, which we have found. Easy. So that is an easy, simple example of second order differential equations. Now let's look at when the trial function doesn't work and you have to multiply it by x for it to work. So let's look at this second order linear differential equation. So this is what we have. So again, let's start off with first finding our auxiliary equation. We get two distinct roots, and so we use the general form of this. Now the trial function that we have to use is px e to the minus 2x, not p e to the minus 2x like we used here, because let's try if we use the general form that we use usually. What happens? So we find the derivative and the second derivative, and then we sub it into our second order linear differential equation, and what we find here is that you get 0. So now we can't compare coefficients because we have 0 on the other side, so it won't really help us in any way. So that's why we try and multiply by x and see what happens. So we have the first derivative and the second derivative, and we substitute it into our equation, our differential equation, and this is what we get. And now we can compare p on both sides, and we get minus 10 over 3. So we do get something for p, and the right hand side is not equal to 0, so we can use comparing coefficients. That's why multiplying by x works. So now that we have a solution for p, we can find our y particular, and we have minus 10 over x, minus 10 over 3x e to the minus 2x. Again, we have to include this x because we are just writing the trial function that we have used, not the general form of what the trial function usually are. And then going back to our general rule, the general y is equal to the y complementary plus the y particular. So the y complementary we have is here, and the y particular we have is here. So we have our solution. And then again, a and b are constants, and usually in questions sometimes what they do is they give you conditions such as when y equals 1, x equals 0, and when y derivative equals 0, x equals 0, or something along those lines, and then all you have to do is substitute into them and solve simultaneously for a and b. But that is again just an additional thing that they do in the exams usually, but it's very simple. I don't think it should be a problem. I don't think it should be that difficult. But yeah, that is it. That is all that you need to know for differential equations for further math. I hope this is helpful. Please let me know in the comments down below if you have any questions, and I'll try my best to clarify them. I hope I have been clear in this video. I will link all the things that I've mentioned down in the description. Please give this video a like if you've enjoyed and if it's helpful to you, so I know what to make in the future. But anyway, good luck with your studies, and yeah, bye-bye.